When you are reading the textbook, you will come across pictures of electric fields. I want to make a point to mention that keep in mind the pictures you see are artistic representations of a vector field quantity. Vector fields are a type of quantity that have a magnitude or a value or a strength and a direction at every location. So we need to specify both the direction of this quantity and the strength of this quantity at every point in our picture. Usually the direction of the electric field is going to be designated with arrows. The strength of the electric field could be designated in a few different ways. Sometimes a whole lot of arrows that are densely packed together will represent a strong field, while only a few arrows that are dilute will represent a weak field. Sometimes a really large arrow will represent a strong electric field, while a small arrow will represent a weak electric field. There are many other ways we could also represent the strength of an electric field. You could do that with the color of an arrow, or perhaps how bold or lightly drawn the arrow is. I want you, though, to keep in mind two things. Number one, remember that the electric field does exist at every location on the page. Realistically, we can't draw an arrow at every location on the page because then you wouldn't see anything else on the page. But for example, the electric field still does exist here and here between the arrows. It just wouldn't make sense to draw arrows at every location on the page. Secondly, I want to say, even though when you look at a picture of an electric field and you see arrows, there's nothing actually moving in this picture. It is normal to see an arrow on a page and think, okay, the arrow represents the direction of motion. However, this is not true. The arrow represents the direction that the electric field is oriented in. To make an analogy, think back to last semester. We said at every location in the room that you're in right now, the acceleration due to gravity is 9.8 meters per second squared, directed downward towards the floor. Even if nothing is moving in the room that you are in right now, I would still draw the acceleration vector as a downward pointing arrow. Nothing is moving, but it is still correct to draw an arrow pointing downward. In a very similar way, in these pictures you see right here, the electric field is drawn pointing to the right or emanating away from the charge at the center, but nothing in this picture is actually in motion. Also, I want to say that don't forget, electric field is a vector quantity. That means we need to treat electric fields as vectors. They combine or add together as vectors. The magnitude and the direction is important when you are dealing with electric fields. So we said that the existence of charge big Q will create an electric field, and then the fact that charge little q exists and can see the electric field at its location means that charge little q will feel a force. However, you might ask, what if charge big Q is not the only charge around? What if there are several charges? How do we treat the electric field from multiple charges? And the way we're going to think about this question is, imagine each charge contributes to the total electric field at a location of interest. So let's imagine there are three charges. We'll call them 1, 2, and 3. Just for simplicity, we're going to assume they're all the same charge. We'll pretend they're all positive. This is not a requirement. It just made the PowerPoint slide easier to make. And we are going to ask, what is the electric field at point X? Now, it is true, there will be an electric field over here and down here and down here to the right. However, we are not interested in the electric field at those other locations. We are only interested in the electric field at point X. So a useful way to think about this question is to imagine that charge 1 will create electric field E1. So E1 is the electric field from charge Q1. We said we'll pretend these charges are all positive. So that means the electric field at this location from charge 1 will point away from charge 1. So electric field 1 will look something like this. Electric field 2 will point away from charge 2, will look something like this. Electric field 3 will point away from charge 3, will look something like this. Now, if I want to be incredibly thorough, I would have to say that at any given location in space, there is only one electric field. You can't have different electric field vectors at the same location. If you go and take some type of instrument that could measure the electric field, you would only get a single magnitude in a single direction. The way we're going to think about this problem is we imagine each of these individual electric fields, E1, E2, and E3, contribute to the total electric field at that point that we are investigating. The only thing we measure with any type of measuring device would be the total electric field. So to find the total electric field, I would have to add these three electric field vectors together. And if I take some type of electric field measuring device, I would find an E total that looks something like this. The electric field at a given point is going to be the sum of the electric fields contributed from each charge individually. Another way of thinking about this is each charge contributes somewhat to the electric field at a given point. Now, because electric field is a vector, I need to add individual parts or contributions to the total electric field together as vectors. Vector addition was discussed in chapter 3-4 of the textbook. So you will never measure E1, E2, or E3 with any type of measuring device. You will only be able to measure E total. However, E total could be thought of as the combination of these three contributions. And if I have many charges around, I could make interesting electric fields. For example, if you look at the picture on the left, you see two sheets of charge that are parallel with each other. Between these two sheets of charge, there is a really strong uniform electric field, while away from these two sheets, there is a very weak, practically negligible electric field. Here we have a positive and a negative charge that are very close together. This was known as an electric dipole, which has its own interesting phenomenology associated with it. And in this picture on the lower right, we have a whole lot of charges that are just randomly thrown about. The blue charges are negative and the red charges are positive, and this random combination makes for an interesting electric field. There are two things I would like to point out here. First of all, notice that in all of these pictures, the electric field lines never cross. Electric field lines are always going to be parallel or infinitesimally close to parallel with each other. Now, you might look at a picture kind of like right here at the center of the picture on the lower right, and it looks like the electric field lines are kind of about to be perpendicular with each other, but this is only a result of the placement and magnitude of the charges creating this electric field. If you were to take a microscope and zoom in, eventually the electric field lines would line up with each other and just be ever so slightly offset from being perfectly parallel with each other. Also, one other comment I want to mention, but I'm not fully on board with this line of reasoning, is that in a way, if you want, you could visualize positive charges as sources of electric fields and negative charges as sinks of electric fields. So you could imagine that the positive charges create the electric field emanates outward, because remember, the electric field points away from positive charges, and the negative charges are the sinks of electric fields. So electric fields will point towards the negative charges and then be destroyed when they reach it. However, personally, I'm not a big fan of this style of thinking about it because, as I said previously, even though you are seeing many arrows on the screen in front of you, there's nothing actually moving in any of these pictures. The electric field has a magnitude and a direction at every location, and when we see arrows, we sometimes think motion, but nothing's really moving in this picture. And when you talk about sources and sinks, that implies something is created at a source and then moves towards a sink, and that's not really what's going on here. However, if it helps you visualizing electric fields, it's not wrong to think about it this way. So to finish off what I want to say about electric fields, the most important thing I'm going to say for the next two slides is this comment on the lower left. The material that I discuss on this slide, you will not see on any homework or exam, because we are going to bring in some calculus here. However, I think it is worth mentioning because it sort of gives you an idea of a good way to think about different distributions of charge. So far, we only talked about the electric field created by a point charge, but what if we have a long line of charge? Or what if we have a disk or a ring or some other interesting configuration of charged particles? So here we have a picture of many individual point charges all lined up perfectly in a nice straight line. And we're going to ask, what is the electric field at that point X above the line? So the way I'm going to think about this is I'm going to say each individual charge, Q1, Q2, Q3, 4, Qn, all of the charges that make up this line will create their own individual electric field at the point in question. And we're going to pretend this line extends infinitely far in both directions. So charge 1 will create electric field E1, charge 2 will create electric field E2, on and on and on until I have accounted for every charge in this infinitely long line of charges. I do realize Q1 is right here and Q1 is not infinitely far to the left, but just go with this picture. Well, from a previous slide, we would say the total electric field at point X is given as the sum of all these infinitely many electric fields that we are considering. We would have to add up an infinite number of electric fields, but in principle, we could think about this is how we would calculate the electric field at the point in question. If we lie very far away, or if we squint our eyes, this long line of point charges all lined up will look like a continuous line of charge. The strategy that we're going to adopt is we will describe this infinitely long line of charge as being made up of many small charges, each of charge dq, all lined up one after the other. Each small charge dq will produce its own individual small electric field dE, and to find the total electric field at the point in question, we will need to add up all of these dEs. An arbitrary charge that's somewhere along this line will create an electric field given by dE equals k dq over r squared. Now, if that charge is further away from the point in question, then it will be a somewhat weaker electric field. If the charge is closer to the point in question, it will be a somewhat stronger electric field, but that's okay. In the limit where the charges become infinitesimally small and the electric fields that they produce become infinitesimally small, I will be adding an infinite number of infinitesimally small quantities. I will be taking an integral at that point. So let us define the perpendicular distance from the line of charge to the point in question as z. Now, we could make a mathematical substitution. Even though the charges that are all lined up in this line at this point are infinitesimally small, we could still meaningfully talk about the amount of charge per unit length. In other words, we could say, even though this really long, infinitely long line of charge is made up of infinitely small point charges, I could still meaningfully talk about there being 2 coulombs per meter along this infinitely long line, or maybe 5 coulombs per meter or whatever. So I could replace the dq with a lambda dx term. Lambda is how much charge per unit length. And if I integrate from infinitely far to the left to infinitely far to the right, in other words, from x equals negative infinity, infinitely far to the left, 2x equals infinity, infinitely far to the right. I'll have to replace r. You could think of r as the hypotenuse of a right triangle. We could find that the electric field created by this infinitely long line of charge could be written as lambda over 2 pi epsilon naught z. To finish off this video, I want to again emphasize that the material discussed in this slide and the previous slide will not be seen on any homework or exam. This is a non-calculus-based physics course, so you will not need to actually calculate any integral for anything in this course that is graded for credit. However, I decided that I want to demonstrate the method of how we think about a distribution of charges that is not just a couple of point charges. It is possible to calculate the electric field for some simple distribution of charges, such as an infinitely long line or a ring of charge. In the next section, we are going to discuss Gauss's law, and we will see that for some special cases with a high degree of symmetry, it is possible to calculate the electric field due to a distribution of charge without having to actually calculate an integral.